Good afternoon and welcome to today's Machine Design webcast. Our topic today is 4 gearing technologies in linear applications and when to use them, sponsored by DieQua Corporation. I'm Jeff Kearns with Inform's Design Engineering and Sourcing Group. To start, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click the yellow Help icon below the slides. Additionally, we welcome your questions during today's event. We'll answer as many as possible during the Q&A session that will follow the main presentation, but please feel free to send your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the Submit button. Also, please be aware that today's session is being recorded and will be available on the Machine Design website within the next week. You'll be notified by an email when the archive is available. You may also download a PDF copy of the slides by clicking the green folder icon in the toolbar beneath the slides. Now let's introduce today's speakers. Roberto Vasquez has been an application engineer at DieQua Corporation for 9 years. His background is predominantly mechanical, but over the years has learned more about AC induction type motors, servo and stepper motors, as well as simple DC brushless type. Tom Cobb's production management experience includes working with internal and external sales group and channel partners to develop strategies and programs for new product rollout and sales activities with customers, distributors, and system integrators. Now let me turn things over to our presenters. Tom and Roberto, the floor is yours.
Thank you very much, Jeff. Much appreciated the introduction. And hello, everyone. Welcome. Today we'd like to put some emphasis on discussing 4 gearing technologies which are ideal for linear applications. So we'll definitely try to bring some awareness to the how, whys, and when to consider the various options. When we talk about linear motion, the idea is you have various tasks that would benefit from a back and forth, up and down, in or out type of scenario. As you can see from the illustrations, you could have a single axis like you see on the ball screw, 2-axis, 3-axis like you see in the other illustrations where you're moving side to side, back and forth, and then you have a vertical element. The idea with this is you're trying to accomplish a linear motion, but what you start off with in many cases is a power source on a servo motor or AC induction motor. And like everybody knows, those types of motors, they provide you with a rotational element. And the idea would then be is to take that rotational element and whether it's through ragged pinion, ball screw, conveying, a belt, chain, and sprocket, you accomplish this linear actuation, if you would. So the focus will be what gear trains will help you accomplish that motion from motor to linear, and also what mounting between the motor and the linear aspect will help you facilitate that aspect. One of the mounting considerations to secure the motor onto the object that's going to give you the linear motion is by using a reducer. A reducer allows you to give you mechanical advantage over what the motor is able to provide. And in most cases, you don't need the full 2,000 or 3,000 RPM from the motor at the load, where a reducer could give you the added benefit of not only torque multiplication, but also gets you into the speed range that you're looking to accomplish this motion. Also, the people in the servo industries, you'll be familiar with inertial matching, right, where this allows you to handle more dynamic handling of rather large loads without concern of overloading the motor. And so in order to connect the reducer onto your machine, one of the common methods, and I'll explain the strong benefits of going this route, is a robot flange, aka rotary output. Synonymous, most people will identify as a robot flange, but for those who don't, also known as a rotary output. And what this is in particular is designed according to the industry mandate, well, the industry norm, according to ISO 9409-1, which defines the main dimensions of a circular plate interface as a mounting plate. In particular, the early on design was intended for end effectors, but has then migrated to connecting other forms of tooling, if you would.
We would, at this point, kind of like to get some feedback from everyone. So scattered through the presentation, we have a couple of poll questions. And this one speaks to when you're designing a rack and pinion type linear motion system, which is the most popular pinion design you would typically select? A straight cut pinion gear, a helical pinion gear, or a roller type pinion. If you could please select or click on the type you typically use, we'll share the results toward the end of the presentation. Thank you.
Excellent. Thank you, Tom. While they're doing that, we'll go ahead and jump to the next slide here. One of the methods to convey rotary motion into a linear aspect is by taking advantage of what we call a racket and pinion. In this case, I'm illustrating two types of pinion gears. As the pinions rotate, they interface with the rack. And you can see the two different profiles. On the left, you'll see the roller type, and on the right, you'll see the helical cut gear. A third one you might be familiar with is a straight cut pinion gear. And the benefit between the three influence reactionary forces induced onto the face of the gear reducer. And so that's the critical thing here. When you are driving a pinion gear along the length of a rack, you have separation forces as you're trying to drive forward. If you were to simply leave a reducer with the pinion gear as you're driving without securing it to a frame, the pinion gear and the rack would separate after, let's say, a few inches of travel. Having the roller type improves efficiency, and it helps with speed. A helical cut gear, while higher torque capacities over a straight cut gear, it induces an axial element as a separation force. So not only do you have separation force radially out from the rack, you also have a thrust force of the gear in or out of the gearbox face, depending on the direction. All right, and so having a ability to directly mount this pinion gear onto the face of the reducer has some advantages that we'll go ahead and further develop those theories. An example of how else reaction forces influence the load on the face of a gearbox is a lever arm. So in this case, while not exactly a linear application, the concept is you have the rotational element of the arm swinging about the pivot illustrated with the circular arrow. So this arm will rotate on a horizontal plane 360 degrees. What happens here is you have a cantilever load illustrated by the vertical down arrow. This arrow has a force that pulls down on the horizontal lever, inducing a bending moment, or if you would, a tilting torque on the face of the reducer. And to illustrate where the reducer would be, you'd focus on the round face of the unit, as illustrated now. And so the idea is by having a robot flange, or like I said earlier, a rotary output, you're able to bolt directly the lever arm, the horizontal lever arm, onto the face of the reducer. And so the idea with the robot flange is you're handling axial load of the downward force In this case, no radial load, but what it is, it's translated or interpreted in the form of a tilting capacity. So these are different applications and how the application induces a reactionary element that the reducer interfacing with the rotary flange are asked to handle. Okay, here's another example. You might see these, in this case it's a pneumatic, what do you want to call it, punch press, if you would, or actuating arm. The concept is more along the lines of the reducers having to do this very precisely, right? So not only are you having to control the angular position, but you have to do it in a precise manner, repeatable manner. So if we were to simply connect to a hollow keyed output shaft, repetition might oblong or wobble out that key. If you were to put a shrink disc on there, you'd have to have some higher quality tolerancing on the components that you're mounting with. And we could go into a little bit further detail. But just to give you a visual of how robot flanges help you provide a more compact solution. Many of you might have experience with robot arms, end effectors. In this case, it's a robot arm, but it might be also seen on a CNC where you might have a mechanism that rotates that supports various tooling attachments or tooling elements for various cuts or various finishes on machined equipment. In this case, having a robot flange allows you to handle the compact need for a limited space in a CNC cabinet. Also allows you to do it in a precise manner without worrying or counting on keyed connections. Then also it complies to the ISO standard. An indexing table might seem like the most straightforward reason to have a robot flange. A robot flange literally allows you to bolt the table to the face of the unit. In many cases, the indexing is occurring on a horizontal plane, but you might also experience it on a vertical plane, in which case the tilting capacity will present itself in a radial manner. In this case, this is can be seen as an inspection table or an assembly table. As the various arms push downward onto the table for a positive connection on the assembled components, you're inducing a force into the table off at a distance, a radius, if you would. In most catalogs, you'll see axial or radial capacities. All these values are indicated on the output shaft of a gearbox, right? Whether you're pushing the shaft in or out of the gearbox, or if you're pushing at some maybe a halfway point on the output shaft. But in order to calculate this type of influence, you should consider that this is a tilting capacity. You have, in essence, that force represented in a bending capacity, so that's where a robot flange would better be suited. So basically what we're seeing here with the various applications that were previously illustrated are what are the benefits of mounting this way, right? You could see that a solid shaft consumes the length of the shaft. So if your shaft is 2-3 inches long, that's space or real estate that you have to account for. And if you're doing a shaft-to-shaft connection, now you have two shafts to account for, plus the length of the coupling that you're going to be using, right? So if you're trying to have a more axial, compact solution, the idea would be to focus on a robot flange. Also, a keyed connection, as opposed to a robot flange, induces fretting. Threading is seen as the consequence or the result of two materials sliding or rubbing, coming into repeated, repetitious contact that over time creates heavy wear marks, sculling on the surfaces. So while in operation, this isn't of concern, but during the assembly time, during the disassembly or time for replacement, you'll experience a great deal of hassle in trying to separate the two. When thinking about other forms of connections, a shrink disc hollow bore comes to mind. In order to consider using a shrink disc for clamping, the idea would be that the solid input shaft that you're inserting into the hollow bore needs to have very tight tolerancing. So this is a burden or an extra step for the customer to have to handle, or for the install team, if this tolerance isn't met. For example, a hollow bore might be a H7 fit, but the shaft would have to be a J6 to minimize the distance that the shaft has to collapse down onto in order to have that positive connection. Right? So whereas a robot flange, you have your standardized dimensions, and everything would then be piloted off of the face. Another reason to consider a robot flange is to allow you to use a hollow bore on the output face. This allows you for electrical lines to be routed through the center, along with water lines. Say you have a water jet application, or for the individuals in the communication industry, right, allows you to run your networking cables for a satellite example, right? Also, as you're routing these elements through a hollow bore, many times you're needing to use a rotary union to connect the various components to maintain signal, or to maintain the electrical feed. And many of those components come at some higher cost, and also there were wear components that by having the hollow bore through the robot flange minimize that maintenance requirement onto the customer, and keep uptime at its greatest. So we focused on the mounting mechanical aspect. So now comes the consideration that robot flanges are commonly understood to require high axial and radial capacities. So they're often produced with higher capacity bearings, whether it's oversized deep groove ball bearings or taper roller bearings. Some units later we'll discuss have cross bearings. But the idea is when you're mounting onto a hollow bore or a solid shaft, you don't accomplish the high rigidity that you would by connecting to a robot flange. And this is going to allow you to handle more aggressive linear applications, to be able to zip back and forth with a little bit more hysteresis, a little bit better repeatability. You reduce the spring back effect from running very aggressively forward, coming to an abrupt stop, and then having the system want to restore its forces, right? Also, because you're not clamping down on a key, you have a zero backlash connection. So for your high precision type applications, where you're looking to maintain position, you're looking to carry out some process that would otherwise be compromised if you had vibrations or some slop in the system, having a robot flange would be ideal. Also, tilting capacities, we consider rigidity in two manners. We have tilting rigidity, right? So while you are expecting the robot flange to have high bending and tilting capacities, right? You also expect it not to deflect. So it's one thing to support the loads, but another thing that it supports it while deflecting. So many times you consider angular rigidity. In this case, there's also the tilting rigidity. I think the first slide we started off with was a rack and pinion design to allow you to zip back and forth in a linear iteration. We also discussed robot positioning and how that could be facilitated by a compact robot flange solution. Water jet applications could be bundled together with laser cutting, for example, or inspection arm, right, or assembly arm. These are applications that would greatly benefit from a hollow bore on the robot flange. This way you're allowed to run the plumbing through, the electrical, the various network cables for communication, to run signal, to gain feedback if you have sensors. The index table can be very diverse. You could see these in welding trunnions. You could see it in robot assembly stations, right? Pharmaceutical filling machines are often used on indexing machines. Say you have various syringes, various packages, various tests that they're carrying through. That's where having a very high precision, angularly stable connection would far exceed over a hollow keyed, hollow shrink disc, or a solid shaft. Inspection equipment, high repeatability. They don't want an influenced reducer to give you additional backlash, additional play that then will alter or change the results. Guided vehicles, right? In these cases, you're having applications under a frame, under a platform, where ideally you'd like to drive the wheel individually so it behaves and maneuvers in the most compact manner. Directly mounting the wheel onto the robot flange eliminates any axial distance that you would get from coupling from shaft to shaft. It also allows for the tilting that you would. You could see that as radial or tilting as you have the wheel's axis horizontal. You have all the weight of the vehicle trying to tip the output of the reducer. As you can imagine, there's also other methods to consider mounting a wheel. But as far as interchangeability, a robot flange far exceeds the counter options. The CNC, this is where I kind of touched on the tool changing, right? You want to hold the part, rotate the part 180 degrees accurately, right? You have a part that's going to be worked on. As it's being worked on and cut, there's reaction forces of the cutting blade onto the part itself, right? You also want to have high repeatability, compact design, and that's just an example of machine tooling. When we work with satellite positioning, you have the chatter or the feathering, right, of the wind pulsating onto the face of the reducer. What this is going to cause is micro shocks on the shaft connections, on the bearings, and so this is where having multiple bolts securing the flange to the satellite would help increase rigidity. And it's this rigidity that will maintain position while those little micro bursts of air are looking to sway the position of the satellite. Right? Also, with the robot flanges, you're able to move accurately without compromising speed. Right? Surveillance cameras, radar dishes, right? More of the same. MRI is big This is utmost in qualities are being requested, the utmost in repeatability and positioning. Having components that are allowing your machine to be smaller is making the market a little bit more competitively attractive to different smaller offices, if you would. So by having equipment that's saving you space goes a long way in trying to give the patient the most positive experience. And so these are a few of the many applications where having the robot flange output far exceeds having a shrink disc or a solid shaft. So many times you're given a list of what industries do these reducers or types of components get used. Here's a very good example of what a rack and pinion looks like, right? And so it's not as simple as a gear in a rack driving up and down. Here you see the value in having a robot. And typically it could be overhead, it could be on the side, and it could be on the base. The forces are similar on the pinion gear as you're driving up and down, but depending on whether it's up top, sideways, or at the bottom, it transitions from axial to radial to tilting. Right?
In this application, as is typical with most robotic systems, cycloidal reducers are utilized at each degree of freedom or at each joint, lending themselves to the axial, radial, and moment support of the load, as Roberto previously mentioned. Typically, the moment arm from the end of arm tooling all the way back to the base of mechanism, in this case a robot, each element needs to deliver the highest degree of stiffness possible with the greatest degree of repeatability. So here we have a combination of gearing solutions. Cycloidals typically used in each degree of freedom or joint on the robot, and a servo precision worm with a robot flange is used to drive the pinion, which moves the robotic carriage along the rack and pinion or the linear guide system.
Well said.
So we have another opportunity for your feedback, please. When you think about the most recent linear application that you've designed, in your application, what type of actuator layout would you regularly use? So of the 4 types of reducer gearing technologies, which one would you most likely use? A cycloidal, planetary, servo worm, or a hypoid? We'll give you a moment to click and select your answer. Okay, appreciate your feedback on that. Thank you very much. Again, at the end of the WebEx, we'll review the feedback you've given us. Thank you.
Excellent. Thank you, Tom. And yes, of course, your results are much appreciated. Excellent. All right. So all along we've been talking about the benefit of having linear motion in a system, how we start off with a rotary supply from a motor, and how a reducer gearbox, gear unit if you would help reduce the size of the motor while giving you more torque, give you an output speed that's lower but still ideal for what you're looking for, and how the reducer itself could offer up an output connection to connect to your machine. This output connection we've been emphasizing is a robot flange, a rotary output, if you would. And that would be advantageous over having a hollow keyed, a hollow shrink disc or a solid output shaft, whether keyed or round smooth. And so there's 3 gear types that easily and readily offer up a robot flange output. That would be a hypoid gear. It provides you a right angle connection. It's a worm gear that also gives you a right angle connection. We have a planetary gear set that gives you inline solutions, and a cycloidal unit that also gives you an inline solution. And of course, you can mix and match, right, to make a planetary or right angle by inducing a bevel to the beginning, or you could put a pre-stage in cycloidal to make it a right angle solution. But focusing individually on the units themselves, we'll go ahead and dive further as to the benefits that each brings to the other. Okay, so let's start off with a hypoid unit. A hypoid unit, you might quickly take a quick look at it and see, well, that's the Bevel Gearbox, so that's a spiral bevel gear, right? You might not be too far off, actually. It's in the name, it inherently says the hypoid hybrid, if you would. It's transitional between a bevel gear, where you would have the center line of center axis of the input gear and the output gear on the same plane, right? So those 2 hashed lines would be on the same plane. As it transitions to the bottom edge or top edge of the ring gear, it starts behaving more like a worm gear, right? And so while the bevel gear is typically 1-to-1 up to about 6-to-1, a hypoid gear starts making its way closer to what a worm gearbox would be, and that's between 5-to-1 and 100-to-1. So in this case, you have the middle point of 5-to-1 and 15-to-1. Okay, the efficiency. The efficiency is 93 to 95%, right? You would ideally have a reduced stack as a right angle. Gives you freedom of compact design. It also allows for a hollow or a blind hole for mounting. It allows you to secure and pilot the pinion gear, for example, or the lever arm onto the unit. Let's see here. The backlash on these units is typically 3 to 5 arc minutes, so you are seeing some ability for precision. A hypoid unit can handle very dynamic and aggressive motion, typically in the constructions and the bearing supports. The robot flange in a hypoid is through a set of taper roller bearings, right? On the much larger units, you could see units going up to 700 newton meters of torque capacity. On the low end, you'll be something near closer to 40 newton meters. These units, because of the spacing and the output, there's a good amount of distance between the 2, the bearing separation. 2 bearings that are sitting right next to each other have a decreased capacity axially, primarily radially, to support outside forces. So by having an increased distance between the bearings, you'll see an increased tilting capacity. All right, so that's good to know. The next unit is a worm gear. This would be the cousin to the hypoid, only that it's able to be more, let's say, output oriented or output axis compact. All right, so basically the gearbox is determined by the width of that bronze gear, and that's a trait unique to a worm gear in that you have a steel worm gear, and then you have the round bronze ring gear, and it's out of a different material to help with efficiencies. Right? A worm gearbox at 3,000 RPM is said to have high efficiency at near 95%, but at reduced speeds, the sliding elements of the worm gear induces a greater effect from friction. On low speed, high ratios, you'll see efficiency climb down to about 40%. Right? So things to consider with low speeds: efficiency will go lower at higher ratios and at smaller sizes. This configuration does give you a right angle output. The robot flange will be hollow. The particular unit that offers this robot flange output offers you very low backlash for those very high precision applications, and then also standardizes on a 10 arc minute solution for those applications that are less precision demanding. One thing to consider with the worm gearboxes is the ability to self-lock. Right, this is a occurrence from the lead angle between the worm gear and the ring gear. When the lead angle is sharp enough, or in this case it's a lower lead angle, it allows for a wedging effect. This is evident in ratios that are 45:1 and greater, as well as gearboxes that are smaller. So just like efficiency, size and speed are influential, in this case for self-locking, it's size of the gearbox and the gear ratio that dictate the lead angle to then warrant whether it's going to self-lock or not. And it is a grayscale, very much at 5:1, 10:1, 15:1, you'll be able to backdrive the reducer. So say you have your linear actuator, your power is cut off, but you're trying to move the table back to its original position. It'd be rather straightforward to apply force on the output table and then backdrive the reducer, backdrive the motor, but it allows you to home in with a power outage. If you climb your ratio up closer to 50:1, 7:1, 100:1, the only way you'll be able to backdrive is by damaging the gears, right? So if you've backdriven a 100:1, the question would be, what happened? And so not only is it allowed to give you self-locking, it's also the quietest of the reducers. The unit, because it's a sliding aspect, allows you to avoid the line contact that you get with helical or bevel or planetary gears. They're always in contact, so they're sliding. And it's also this sliding element that influences the efficiency. Of course, if you guys have any questions about the difference between the worm gear and the hypoid, feel free to pose the question and we'll answer it later in the presentation. Okay, the next reducer that allows you to have a rotary output flange is a planetary type. This planetary gearbox gives you a inline concentric solution. It gives you, in a single stage, a ratio between 3:1 up to 10:1. And here I am illustrating 100:1 as the high end, but this is simply because you could do a 2-stage. On occasion, you have seen 3-stage planetary units. Many times, we partner a planetary gear with a worm gear to allow you right-angle compact solutions that could handle high speeds. The planetary input gear, you can see on the bottom, top right, it's the gray gear in the middle, and it's driving the blue the blue planetary gears. They're inside of the housing, which is the annulus ring or the ring gear. And so the reaction forces between the input gear and the output give you, at a minimum, a 3:1. These units are said to have efficiencies between 92 and 96% efficient, and it's not speed dependent. These units are in essence comprised of either helical gears or spur gears. They're constructed in such a manner to be called the Planetary Gearbox because they're 3 gears surrounding a central gear, much like planets revolve around the sun. The units that offer the robot flanges in the planetary units are offered in 3 levels of backlash, 3 to 1, as low as 3 arc minutes and as high as 15 arc minutes. Because of the sun gear, we're able to handle high inertial loads. We're able to accelerate quickly. The sun gear itself is a low inertia component because it's only the diameter of the gear itself. Planetary units are wide berth as far as what sizes they're offered in, small as 3 newton meters all the way near 1,600 newton meters. The robot flanges are offered in taper roller bearings and an option and a different model to go with ball bearings as well. So I spoke to the compact design of a planetary. The front-on view, this is important when you consider something compact or not. A planetary on a front-on view is limited by the OD of the face, but and that's great, right? It's only as big as the face of the unit, but the length is what considers to be the maybe not so compact design. So it depends. You have radial distance that you could have freedoms in, or is it axial? And if it's radial freedom, then you'd want to go with the right angle solution. The fourth gear technology that we're considering is the cycloidal unit. This particular unit uses an intricate design in which you have oscillating eccentric bearings creating 2 plates that are transferring motion on what we consider a transfer component, transfer member, and it allows for a set of needles to walk the circumference of the housing which supports the pins, right? So the idea is as these 2 plates are oscillating on the eccentrics, it's creating a walking effect on the pins to the needles. So you always have one less needle than you would have channels. And what this does is it's always in positive connection. So in case of a jam, you're not going to have the loss of the load. And you're also able to have very high torque dense solution. So very compact axially for the size, the highest torque capacities. Because it's internally constructed across bearings, taper roller bearings for the input shaft, it's able to handle by far the greatest amount of axial, radial, and bending capacities that you could throw at it. It is a very smooth operating unit because of the oscillating motion. It's not coming to abrupt contact like you would get in a helical gear, a planetary, and a bevel. You can see the range of sizes, something as small as 50 millimeters, near 2 inches, all the way up to 335 millimeters to give you a good understanding of how this unit varies in sizes. Through the various combinations of rollers and needles, you could accomplish the ratios 41:1 all the way up to 125:1. It does lend itself to having a hollow through on the through the body for allowing the plumbing of the components, and it also facilitates mounting of the reducer itself by having the outmost flange. Anything you want to add to the cycloidal unit?
The cycloidal units, as compared to a flex spline design, lend themselves to roughly 3 to 4 times the torque capacity because of the trochoidal reduction mechanisms that are within the units. What this speaks to is in the instance of a torque overload or the amount of rotational force as compared to the size. We refer to that as torque density. In combination with the twin cycloidal drive system, the use of cross roller bearings on the output flanges lend themselves to being much higher mechanical capacity in a smaller size. Generally, if we compare size to size, will be 2 to 2.5 times or higher in mechanical strength capability. Roberto, thank you.
Excellent, thank you. So we've touched on 4 gear technologies, all which offer a robot flange output. The benefit of the output being a robot flange facilitates positive connection that won't allow for fretting, connection that will give you bearing support for those high radial and axial applications that have high tilting requirements, right? And so by going with the robot flange through one of these various gear technologies, you're able to better design your machine, give you more compact design, right? Better maintenance, so reduced downtime, better cost of operating the machine, and also because you're eliminating couplings, you're eliminating high precision tolerancing on insert shafts, you're also reducing the cost of the design of the construction, right? So this is also better for purchasing, less components to document, and the list goes on as to the various benefits of the robot flanges in these gear reducers for the linear industry.
Roberto, thank you. We want to bring up a couple of results from the questions we posed earlier in the webinar. When you're designing a rack and pinion linear motion system, typically which pinion design would you select? And a helical cut pinion gear was the leader by about 43%, followed by a straight cut pinion, and then third place the roller pinion type. As Roberto mentioned during the event, the implication of using a helical cut pinion and rack system not only induces separation forces that the reducer will see as a moment load, you also, because of the helical structure, will see a separation force or an axial push or pull in and out of the reducer. So having sufficient bearing capacity not only to contend with separation, radial, or moment, we also have to think about the axial load in its consideration as well. The second polling question, when thinking about the most recent linear motion application, that you used in actuator layout, of the 4 types of reducers, which technology are you most likely to use? Not surprising, Planetary came out at about 45%, servo worm at 24%, cycloidals 21, and then Hypoid at 23. Each of these lend themselves for a variety of factors in positioning or configuring relative to machine or application footprint, but then also bearing structure and support capacity also comes into play. Roberto?
Excellent. Thank you. Well said. I think we have some time for some questions. Maybe now would be a good time for some questions.
Yeah. Thank you. It looks like some of you have already submitted some questions. If you still have a question, please type it into the question window on the side of your screen and hit the submit button. And while we're answering your questions, please complete the feedback form, which is located on the bottom of your screen. And the first question, do you offer two-stage cycloidal reducers?
All right, excellent. Good question. Yes, so one of the previous application we had was to lift the table up and down, and it was going to be packaged into a vertical column. The idea with this is to give you the robot flange capacity of the cycloidal unit, but also bundle it in a vertical column, even though the output axis was horizontal. So our idea was to package this with a right angle worm gearbox, right? And so in this case, we were able to, as a pre-stage to the cycloidal, connect a right angle worm unit and secure it in a radially compact design so it fits in a vertical column. Good question.
Okay. And of the four solutions you talked about, which is the ideal pick for food packaging machinery?
Okay, so that question begs some understanding of the food industry, right? Food industry, of course, sanitization. Secondary is ability to withstand the harsh cleaning solvents that allow you for a sanitary condition. Not only that, but also minimal nooks and crannies, if you would, where bacteria might harvest itself and grow. So that idea would be more so along the lines of which of our gearboxes offer ability for coatings, ability for material changes that are more resistant to corrosion, right? And so from the ones we've considered, the Hypoid unit allows me to do what we consider a QPQ process, quench, polish, quench, and it gives you a surface finish that allows against corrosion, right? It also has plates and machined surfaces with reduced cavities, and we could swap out the hardware to be stainless steel. The worm gearbox allows itself for coating with various paints, while the Planetary and the Cycloidal probably better suit themselves the best, being that they're circular, they have many clean surfaces, and then can be offered in perhaps a nickel-coated surface. Well, another very good question. Thank you.
Okay. This one is, what about harmonic drives? Apparently they mentioned I used to apply them for gimbal mounts.
So when we look at applications that require ultra-low or zero backlash, the two predominant technologies that exist out in the industry, one being a flex spline construction, the other the cycloidal configuration, each have salient capabilities, generally in gimbal type applications, depending on the application, whether it's earth or ground based or aerial, then comes into question of the amount of weight that the vehicle might need to consider. But when you also look at applications, whether it's surveillance, antenna positioning, security, an automated weapons station, the ability to tolerate reaction forces or recoil forces, a cycloidal design with its cross roller bearings and the twin tricloidal wheel construction has a much higher capability to tolerate those reaction forces, so it gives you a more stable, smoother operation. Great question, though.
And this one is, rotary flange is a gear unit or a motor?
Right. So earlier we talked about how the motor gives you the rotary motion, and in order to minimize the size of the motor, we introduced a gear unit. A gear unit could also be known as gearbox or just gear reducer. And so in this case, it's the gearbox that would offer the robot flange. It's the output of the gearbox that would be presented in a robot rotary flange method. This way, it allows you bolts directly to the machine or to the structure that you're looking to rotate. So if you're going to think the drivetrain, it's motor, gearbox, robot flange, which is in essence the output of the gearbox, and then you'd have your conveyor or your machine, your linear actuator that you're looking to drive. Yeah, that helps clarify exactly what components are what and how does everything play together. So, good question. Thank you.
And what are the center distance constraints or parameters for internal gears for a hypoid?
Okay, so let's see here. The hypoid unit, right, because that's inherently how the units, funny enough, that's how they're sized. It's by the offset and gives you an idea of how big they are. So the units that we're talking about, the hypoid unit, we're talking about units that go as high as 740 newton meters, right? So 700 newton meters is then dictated by it. Roundabout, it's dependent on the gear ratio also, but you should see it around 40% off-center.
Okay. And can pulleys and belts be used to connect linear ball screws and stepper motors?
So in applications where a ball screw type linear actuator takes advantage of the lead pitch to drive nut, yes, a pulley and timing belt can be incorporated. However, when a step motor is utilized within a linear actuator, particular caution needs to be exerted with regard to the tensioning of the belt, as this would induce some additional resistance to movement, and if it is a repetitious design, in the case of an OEM, caution needs to be exercised so that the exact same tension is applied every single time to have consistency of performance on the leaded actuator.
Very good question.
And this will probably be our last question. I'm going to just try to combine the two because I actually like these. It is, one, how do these units compare cost-wise? And two, are there speed limitations?
Very good points. When I discussed the Planetary, I discussed the rather small size of the sun gear. So speed limitations are influenced by lubrication, ability to maintain lubrication when things are spinning so fast, oil wants to fling itself off of the gear face, right? And so oil film becomes very thin, and then the friction elements kick in a little bit more, heat transfer gets a little higher. And so units that minimize the pitch line velocity, basically the diameter, the distance traveled in one rotation, a bigger item travel one rotation induces higher linear speeds. So a small pinion gear is better equipped for higher speeds. So from the various technologies, I would consider the Planetary gear type to be the best suited for high speeds. Second, I would probably make a close call between the Hypoid unit and the worm gear, right? In the case of Hypoid, the 15-1 would be far suited better suited than a 5-to-1. The 5-to-1 would have a bigger pinion gear. The worm gear, the OD of the worm gear is relatively the same. So from that standpoint, it doesn't change ratio-wise, but as you can see, a worm gear is long and narrow, so it is very good at collecting and trapping the oil between the gears, right? And then to consider costs, right? The added benefits that the cycloidal unit offers: zero backlash, excellent tilting capacities, excellent repeatability, in allowing you to give you the utmost for those most demanding applications. Torque for torque would be offered with at the higher price, and then you'd probably look at the Planetary to be on the lower end. Thank you.
Okay. All right. That will conclude our presentation today. On behalf of Machine Design, I'd like to thank DieQua Corporation for sponsoring today's event, and of course all of you for joining. Have a great rest of your day.